Hello viewers and welcome to another episode of Space Science with Python. Today is the very first video in our space science tutorial videos where we will use a deep learning library to create a neural network for our multi-class problem. So we will use Keras or TensorFlow to distinguish between our four main group asteroid classes C, S, X, and the other. And for this, we are using, again, also Google Colab. But if you would like to do this offline on your local machine, you can also do it. The computation or training is quite fast. It only takes a couple of seconds, maybe maximum half a minute or so. So yeah, if you are making a pull from the repository, please note that the requirements txt changed because TensorFlow has now been added into the requirements txt for virtual environments. Keras and TensorFlow, I will provide the links into the description. Here is the Keras website, and Keras is now part of TensorFlow as a submodule. We will not dive into how neural networks work. I think there are tons of amazing tutorials, videos, animations, and blog entries how neural networks work, how the training is being conducted, what backpropagation is, and the gradient descent, and so on. So I hope you're a little bit familiar with neural networks. If not, don't worry. Just get some small tutorial or so, get through the basics, and you will understand today's video. Because in today's video, we will not use any fancy layers or so. We will simply use dense layers, so simple, I would say linear combinations of functions. So it's not really I would say deep learning in the sense that we have like thousands, or not thousands, but a lot of several layers with convolutional layers and maybe a mixture also with LSTMs. So no, today it's, I would say, quite shallow. We will only use the dense layer to warm up a little bit with neural networks and to make you a little bit comfortable and familiar with the concept of neural networks, or also programming with Keras. And of course, if you have any questions or if I do any mistakes or so, always feel free to send me a mail or comment or send me a DM on Twitter. Now for our video today here, we are creating a small neural network. And I would say, let's start now with the coding. And we have our four, I would say commonly known cells in the beginning where we import our libraries, where we are mounting G drive and then also reading in the level 2 asteroid data and then putting them into a NumPy array. And the first thing is, of course, that our asteroids Y value list is, of course, an array with some strings, with the C, S, X, and the other. And we need to convert it into some kind of integers because our neural network expects integers as classes. And there are two ways to do this. So the first thing is we can map, for example, each class to a certain integer, like C becomes 0, S becomes 1, X becomes 2, and so on. But we will use something called one-hot encoding. And one-hot encoding is something we will use to put it into our neural network. And I will tell you a little bit later also why we will use this method. But before, I would suggest let's create our one-hot encoding, and then I think explaining is easier when I show you a concrete example. So here we are initializing our one-hot encoder, and then we are converting them to asteroids. I call them one-hot, so O, Y, so the labels, and then I will call the label encoder, and then I fit and transform immediately the input data, and this is the asteroids Y. But for scikit-learn, we have to reshape it accordingly, and then we want to have it finally as an array. So let's put it like this. And maybe let's also print out what the results are. So there we are. We have our one-hot encoding, and you see now that we have, we have for each spectrum, we have a row, and this row contains 4 entries, and because 4 entries because we have 4 classes, and the 1, 0, 0 corresponds to a certain class. Let's have a look at the asteroids Y. What is the very first class? I think it was the C class. Exactly, it's CC. So C is the first entry. S is, yeah, as you see here, the third, and X and other are probably then 0, 1, 0, 0, and 0, 0, 0, 1. Of course, this is now something I show you now here to show you how to work with scikit-learn and how to do it. But be aware that if you are creating a neural network or a model and you would like to deploy it or provide it to others, you also have to provide this encoding. So there are 2 ways. The first way is, of course, to store this encoder as well. Otherwise, it may become useless for others because they don't know what is 0, 1, 0, 0, 0. Or you create some kind of configuration file or JSON file where you're simply hard coding the C class, the different classes to some integers or to one hot encoders. So you provide either with your machine learning model, you provide the encoder class as well, or just this JSON file where you have the encoding. But it's rather important to see how this is stored. Now, the question is, of course, how are things now encoded? We can also simply, iterate through it. Let's do a more coding way. We create some initial one hot encoder encoded list like 1, 0, 0, 0 here in the first line. And now we iterate over a range of 4, so 4 classes. And what we do now is we are simply rotating the initial list to see what we have in there. So we are simply rotating them by changing the position and reshuffling it, and then we say, okay, what is our original class? Well, we can use again the label encoder dot inverse transform. So this is the command that's important to recompute the original classes. And then we see, for example, how can we say this? I would say one hot, and then we can print the one hot class we have here corresponds to the class, and then we have the original class, and I think it's a nested array, so I have to assign, I think, 0, 0. Let's see. And there you go. So here we have now our classification. The 1, 0, 0, 0 corresponds to C, 0, 1, 0, 0 to others, 0, 0, 1, 0 to S, and 0, 0, 0, 1 to X. Of course, I just said we can also make an integer encoding, like C becomes 1 and so on, but yeah, just stay with me with the one hot encoding. I would like to talk with you later why I prefer this way. But again, there's no good or bad or so, it's just personal preference, I would say. Now we have to make our stratified shuffle split. You may remember it from last time, where we shuffled our data set into a training and test set, and also considering the classes that are in there. So we have to be aware of this. So, okay, I'm back because I just wanted to put the stratified shuffling into the clipboard, so I don't have to rewrite everything, because we used this script part, I think, now a couple of times. Now we are making now the stratified shuffle split with a test size of 20%, and then we assign the data to the X-train and the X-test, as well as the corresponding classes. So we have here now our corresponding classes. Let's have a look at the one hot encoded values, and there we are. So we are now good to go to create our neural network just in a moment. Because the thing is now, our data is of course unbalanced. Yeah, so we had our input parameters and scikit-learn and support vector machine to consider different weights for our classes. And the same thing applies also here for Keras, where we can provide also class weights, so we weight each class differently, or we are computing the sample weight. So we assign a weight to each individual sample, and we do this here with the sample weight, because for the class weight we have one hot encoded values and not like integers, so we use the sample weight. And to compute a sample weight, we use a function from scikit-learn that is simply called compute sample weight. And the sample weight is then simply computed. We just call the function compute sample weight, and we just call or put in there our training data. So y equals to y train, and there we are. So these are now our sample weights that are being considered in our neural network. And now it's time to create our neural network. We are first of all importing Tensorflow Keras as Keras. And you will say, wait, where is the standard scaler? We need to scale our data. And this is the good thing about TensorFlow. We have normalization or scaling layers in our neural network, or in our layers. So we don't have to do it with scikit-learn or so before. Now, first of all, I would suggest we are assigning the numbers of inputs. This is important for our input layers, so that scikit-learn, Keras knows what is the shape, the input shape of our data. So we have 49 wavelength steps from, I think, 450 to 800 nanometers or so. So this is the number of inputs we have. So if we just execute it here and now, print it out, that should be 49, and yeah, it's 49, so we are good to go. For our model itself, we can now simply write here our different layers and so on, but I would suggest to create a function, because the first thing is we will do 2 training steps. The first training step is we will just execute it over, let's say, 300-400 epochs and compare and see how is the loss function and the validation loss behaving. Yeah. In the future, we will not do this anymore, or maybe just once in a time, just as a small reminder. But here I would like to show you all the epochs, but the final model is then computed from the final step. Afterwards, we are recomputing the model, but we are stopping our training at the point where overfitting happens. And well, you might ask, okay, when is overfitting? How can we prevent this? Just stay with me. We will first create the model, and then we go through it step by step. So let's create our function called create model, where we first create something like I would say a normalizer. So keras.layers normalizer. This is, normalization along the axis of 1. So this scales our data accordingly. And it's also important to know that before you don't fit the normalizer, you have to first adapt it with the X training data. Now we are creating our input layer. So with keras.input, and important to know, important for you, there are 2 ways to create Keras models. First is with the functional API, and the other one of model API, and the other one is with the sequential. We use here the model way. So we have our input, and what is the input shape? It is, of course, the number of inputs we just provided. Good, and now we can create our first hidden layer. So the hidden layer, the first one, is actually our normalization layer. So the normalizer that takes the input layer, and then we can create our dense layers. So the first one, again, I will just say something in a moment regarding the structure of the layers and so on. So we take 25 units here for starters, hidden layer, and then we use an activation function. So I also suggest to use the activation function after the dense layer, because if you would like to add batch normalization between them, it's easier if you are simply separating all the functions individually. So we have here now the ReLU function, like the very common one, and then hidden layer. So the ReLU function is quite simple. It's simply a linear function that is goes from 0 to infinity. But if the values are negative, then the output is set to 0. So there are also like leaky ReLU functions that have a different slope for negative values. I think we can play around a little bit with it. So our case today is not, or our scope today is not to create an extremely powerful neural network. It's more about the concept. And of course, I don't want to provide here the best solution for the neural networks. It's also a little bit task for you to play around with what I provide here, so that you get a feeling and understanding of how these neural networks work and how the loss functions are being affected by different parameters and layers and so on. So here we have simply the two hidden layers with the 25 units and 10 units. And now we can now create our output layer. And the output layer is again a dense layer, layers.dense. And the number of units that are being the output units is 4, because we have 4 classes in a one hot encoding. So like the 0, 1, 0, 0 class, for example. And this is the nice thing about one hot encoding. So the last layer will not provide us a result like 0, 1, 0, 0. It will provide us probabilities for each class. So this is what I like about one hot encoding. You can also make some analysis on the statistics, on the probability statistics that is being provided by the neural network. So I like the way how it creates output. So, but again, there is no right or wrong. It's just maybe also, yeah, how you like it, but I like it. So this is our last layer. And then of course we have to create our model itself. It's not being created yet. So keras.models model, and then the inputs equals to in the input layer, and the outputs correspond to the output layer. Okay, I think I'm done. I need to return the model now. Now, if you would like to play around, you can simply play around with the function and then see what kind of effects are happening outside. We are now calling the model, so we assign it here to model, and now we have to compile it first. So there are different optimizers. We just take one of the standard one, the RMS prop. There are also others like the Adam or so. Maybe also here, try around, play around, or get also a little bit the block entries, what the different optimizers do. They adjust for different orders of momentum and so on. So it's a complex story. The loss function is a categorical cross entropy. If you have, for example, not a one hot encoded, but simply integers like 0, 1, 2, 3, 4, and so on, you need the loss function sparse categorical cross entropy. But here we have our one hot encoded thingy. Now let's take a summary of our model. Here's our model being described. And the number of trainable parameters is around 1,500. So this is not a lot. This is really just a very small model. And let's see whether this model even has a good performance or not. You can really extend it with thousands of layers, but yeah, it's an overkill probably. So just stick with maybe 2, 3 layers and don't exceed, because at some point you will not not optimize it anymore. We will compute for 500 epochs with a batch size of 32. I will say something about the batch size just in a moment. So for 23 batches, or one batch with 23 spectra is put into the training for backpropagation, and then the next 32, then the next 32, and so on. So this is what stays behind the batch size. If you put a too huge number, it may become a problem for your RAM, but not in this case. I mean, we're talking about very small signals, but if you, for example, computing video data or so, this you have to really be careful with this. And with a higher batch size, you have also a higher accuracy to adjust for the weights adjustments. So let's create our model. We would like to take the history log of our model fitting. So we put the X train in there and the Y train. The number of epochs is the epoch we just defined. We would like to have a certain batch size with not 32, with batch size. Exactly. You can also adjust whether the Keras should provide an output or not. Let's see what it does. Verbose equals 1 will provide us an output. In the GitHub repository, I will put this to 0 because I don't want to spam around the output cells. Our validation split is now 25%. So what does it mean? Well, we have our stratified split here. Where is it? There. 20% is now the test size. So which means 80% is the training data. And 20% of this 80% corresponds then to a validation size of 20%. So we have 60% training, 20% validation, and 20% for testing purposes. And it's always important to have a testing data at hand, because using validation data, it's somehow also leaking information while the training, and then you get a bias, or let's say you get a better result or the results appear to be better than they actually are. So I would suggest let's start the training. And there you see, it's now running with all the output, and this may take some moments. Okay, the training is now finished. You see each step took only 4 milliseconds, so that was a very fast training. I'm not scrolling now through the whole history log, but you see the output is spammed with all this thing, and we see it's quite a fast computation, so we can put our value verbose to 0 so we don't get all the information all the time. But before we take a look at the loss function, let me say something about the batch size. So the batch size, you see maybe in online tutorials, batch size always taken like 32, 16, 64 and so on. So multiples of 2. And it's like a common number. But what does it mean? I mean, you put 32 batches inside for the first training, then the next 32, the next 32, the next 32, and so on. But the length of our training data is not a multiple of 32. So if you want to check, you can create the modulo of this. So the batch size, and we have like 15. So the last batch is 15. And it's not really a huge problem, especially with a huge data set like this one. But be aware that the setting a batch size a little bit wrongly can cause some kind of training bias, just for you to know. And now we can plot our loss function. So as always, let's use matplotlib again to conduct this plotting. So we use pyplot as PLT. And of course, you know me from my last videos, I like the dark mode. So let's set the dark background. And then we create a figure. And now we can plot the loss function of the training and the validation loss versus the epoch. So the epoch is starting at 1 and goes until the end epoch, I think what's called, and epoch plus 1. Let me put this into the clipboard for later. And then we have from our history log, history. First of all, the loss. And let's set also some colors to distinguish a little bit between the both loss functions, and also setting some kind of label. Training loss. Maybe I can copy paste this entire part here. So I think this is now val loss. We use maybe green, and here validation loss. And then of course we want to plot the legend so we don't confuse ourselves, as well as some X label, which is simply called epoch. And on the Y label is, yeah, simply the loss. So this should be fine. Let's take a look. And what do we have here? Well, this is really, really bad, I would say. But yeah, let's see what these curves mean. So we see our training loss is decreasing over time, and this makes perfectly sense because the neural network tries to fit the data and better and better. But the thing is, we want to generalize our training. So we would like to find a model that finds general rules. So for example, if you take a picture of a dog or a cat, we want to have an algorithm that understands the concept of a dog. So what makes the shape of the dog a dog? Like the ears, the eyes, the overall appearance. But if you are overfitting, then the algorithm with the dogs and cats will consider maybe also the background. So for example, some snowy landscape from the husky images. So yeah, snowy landscape is also important because there is no cat outside. We have no images with cats in the winter landscape. This is an overfitting because this is like ridiculous information for our problem. And this is where our validation data goes in. So our validation loss also improves over time, but it reaches at some point a minimum, and then the loss increases again. Yeah, see here, this is also quite bad. It should be a little bit better like this, but yeah, maybe our simple network is a little bit too simple, I would say. So this is the region where our network finds its generalization. So here, and afterwards, it starts the overfitting. So our best solution is somewhere here in this region. And now our last model has been trained. And so our model corresponds now to a validation error somewhere here, which means we have to retrain our model. But this is not a problem because we can set something which is called a callback. So we don't have to zoom in and see, okay, is it epoch 80 or 90? I mean, it will change all the time anyway because of the random initial weights. So we need to stop our training with a callback called early stopping. So what does early stopping do? It monitors a certain metric, for example, the validation loss, and it has a certain patience. So it sees, okay, maybe it improves. In the next step, it becomes a little bit worse, but then it improves again. So it would stop too early by considering these small spikes here in between. So we wait for example, 10 epochs. It's a little bit much. 3 or 5 is the common rule, but let's set it to 10. And then we can retrain our model. So let's say create model. We compile it again. Maybe I can just simply copy paste it from here. There we are. I don't need everything. I don't need the model summary though. So this is also defined. And in the fitting, we have now our callback. Actually, the input is called callbacks. So you have to provide a list, and in our case, it has only one entry, namely es callback. So we can run it now. Verbose is 0, so it will not spawn any output. So it trains now, and we can see how this works. I mean, we can maybe retrain it with 1 to see how many epochs it ran through. Okay, I could have taken the history. Yeah. Anyway, let's see. I think after 80 or 90, it should stop. So let's see. Oh, even 60. Okay, cool. So we can stay here. But yeah, the validation loss is a little bit high. So we can maybe play around a little bit later with our model to see how we can improve this. Now, the next thing is, of course, we want to make a prediction of our test data. So first of all, we compute not the prediction classes, but the probabilities, as I mentioned. So we'd say model.predict of X test. And if you print this out, you will see we have for each row is a test spectrum, and these are the probabilities for the one hot encoder. So the first one is probably not a C class, it's more like this one here, and the sum of each row is always 1. Yeah, so this is how we can now test our data, but we have to convert it first to our one hot encoder. So for this purpose, we can first create an empty matrix or empty numpy array. So zeros. There's a command like, so I can just put in there this here. So it takes the shape of it, and then we compute matrix of zeros, and then we can say, okay, go along the row axis. Where's the cursor? There it is. Go along the row axis and take the maximum per row, the argmax, and set it equal to 1. So the rest remains 0 because, yeah, we defined the 0 matrix here. So let's see how it looks like. This should be our final result. So this is our result now with our one hot encoded results from the test data set, of course. And now I would say let's compute again our matrix we know from last time, like the confusion matrix, but not with the one hot encoded, but really with the human readable format, the C, X, S, and other class. So we say asteroid classes underscore test. We take the label encoder, just as a small reminder how it works, with the inverse transform of the Y test, and we have to reshape it. So the result -1, 0. So how does it look like? Let me see. Yeah, so this is now our test classes, and now our predictions follow afterwards. So test prediction, not Y test. This is called Y test one hot prediction. Okay. Okay, there is the next cell. And now we can plot our confusion matrix. Maybe from last time, you know, the function from scikit-learn is deprecated. So I did some research and found some new functions that should be used in the future. The one is called confusion matrix display, but our confusion matrix command is also still needed. So now we compute the confusion matrix, where we say confusion matrix of the asteroid classes test and prediction. Test and prediction, and then also the corresponding labels we can assign. So we have, what classes do we have? C, S, X, and the other. Cool. So now we can display the confusion matrix with this confusion matrix display command. So confusion matrix equals conf mat, and then display labels is also equal to this array here. Okay, and then we can say disp plot, and then plot show. I think plot show is not necessary, is it? I don't know. I will not play around now. Oh, I made a mistake. Labels. It's labels. It's labels. And there's our result. So we have here our true labels versus the predicted label. And we see here, for example, the predicted label C and true label C. Oh, this looks really good. Only some deviations. We have C and C, X and X and other. But we see that some others, so they are predicted as other, they are actually S class. So our F1 score should be, let's see, maybe only around 90% or so, but I would suggest also to compute the F1 score. F1 score, you know the command from last time, sklearn.metrics.f1 score asteroid classes test and test prediction. Average is weighted. Oh, there is a, I should make a line break here. And yeah, rounding it to 3. I think I always did 3. Let's print it. And we have, oh, okay, let's say it's 92%. So, or 0.92. Fair result for a very simple neural network that consists only of these 2 layers with 25 and 10 units. And it's simply a dense layer. So we don't use even convolutional layer or whatsoever. It's, oh, I see there's also a mistake. Why didn't oh, is it maybe let's rerun this. I think this shouldn't be a problem, but it's very strange that there was no error spawn here when I saw it activation. So let's rerun this maybe. But I think, yeah, I don't know why this, maybe when I executed it, it was written correctly and then I rewrote it or unintentionally I deleted some characters. Could also be. Okay, still running. I'm not making a break now. Let's just wait for a few seconds when this is through. Because we saw that the output worked actually, so this should be fine. But maybe it just took a dense layer without any activation. But I don't believe that. I don't think so. We will see the results just in a moment. And it's through. So let's rerun our... Yeah, okay, it didn't change a lot. Maybe it improved a little bit. I don't know what happened actually by writing a wrong word. I don't know if this was even considered because it didn't spawn any error. So yeah, it's quite difficult to understand. Okay, guys, I see the problem. This is called it's called create model, and I called it create mode. So this is the problem. And you may think, wait a second, how can this work? Well, I just tested some architectures before this video to see whether we get some sufficient results, let's call it them like that. It was actually this architecture here, but the name was different. The name was simply called create model and not model mode. So it was still in the RAM of the server. So we can now here rerun everything. I think this was actually the mistake. I apologize for this. I hope you can forgive me because this is also the reason why it was marked. I didn't see it. because there was still in the cache from the last session where I just tested some architectures, and I just decided to make this 2-layer output. But I think this is fine. I hope you're fine with that. So my suggestion would be now. I will now rerun the entire notebook, and let's see at the final results again. Again, it was this model, so it shouldn't be changed. What we can do now, maybe before I rerun everything, maybe let's add a layer before. This is so we can maybe check the difference. So let me restart the runtime, and then I run through this entirely. Okay guys, I'm back again, and I just retrained everything with a layer more. We see not a huge improvement of the validation error, it just took more epochs until it started overfitting. And now I'm making here this callback thingy again. It also ran through it, and we have again our F1 score now at, now 96, at 0.96 almost. So again, I apologize for the small error, and this should also be a warning for everybody working with Jupyter notebooks. Jupyter notebooks are nice and fun for demonstration purposes. I mean, here I use them because they're interactive. I can provide markdown recipes into my scripts on GitHub and so on. So they're perfectly fine for education and for showcases and so on. But be always aware of these issues like I had them here in production. So in production, it can be a pain if you have something still cached somewhere and you're working on under wrong premises. So this is that can be a pain. But again, this is now our first small dense model. I think next time before I start, I will reset the runtime. But yeah, I just checked the GitHub script just a moment ago, and it appears to be fine. Now, you see here, now the question may be, okay, how many layers should I have and so on? What about regularization and so on? Up to you, yeah? Now, change the layers, use maybe a leaky ReLU, use batch normalization, use a dropout. So batch normalization is mostly between the dense and the ReLU layer. The dropout should be then after the ReLU layer and the next dense layer. So just as a small hint, let's say these are like the best practices. Try around other architectures. Also here, there's still a lot of room for improvement, like our k-fold. We don't have really a k-fold cross-validation. We simply, split it once and that's it. And also in our future videos, we will create more sophisticated models. So the next time we will use convolutional layers to show you how it works. And then we will also go a little bit through other metrics of imbalanced data sets. So TensorFlow has a very nice summary of all different metrics for imbalanced data sets. I provide the link into the description. Feel free to go through it. It's really worth the read. For such a video, it's a little bit of an overkill, I think. And now, what else do I want to say? And there are also different ways. Like, for example, we have now a dense layer. Next time we can create a convolutional layer, and then you can create something like an ensemble of layers. So you have one model with a good performance and another one with also good performance. You can merge them together into one model. You get then the you can take the average prediction or so, but also considering the validation loss. You see, I could now talk a little bit longer now. I think we can call it a day. Feel free to adjust the architecture a little bit and play around. Especially, it's I think the book Deep Learning with Python by François Collet. He also said in one of, I don't want to quote him now. It's like more how I recall it, that sometimes creating architectures is also a little bit like an art, because it's also based on a lot of experience and so on. And for each case, there is no strict blueprint how to create neural networks. But here we have a starting point. I hope you get familiar with it and comfortable with neural networks. And I would say happy coding and see you next time.